In this video, we'll look at more complex rational functions. So if you haven't already, I would definitely recommend checking out the intro to graphs of rational functions, as this is very much a continuation of that. We're going to look at some more complex and complicated examples. In particular, we're going to be looking more at the end behavior piece and the horizontal asymptotes here. So let's talk about hypothetically how we would graph y equals 1 over x squared minus 25. So as we talked about in the last video, there's a couple components here that we have to address. We have to address vertical asymptotes and we have to address any horizontal asymptotes. So remember that if we're looking at vertical asymptotes, we're looking at when this is equal to 0, the denominator being this. So if I'm going to go ahead and set x squared minus 25 equal to 0, there's a couple schools of thought here. Number one, you can factor. So you could say x plus 5 times x minus 5 and say that equals 0, and then that would result in x being plus or minus 5. Or the other option being you can add 25 to both sides and then you square root, which again gets you plus or minus 5. Now we have to just be very careful to make sure that we acknowledge the possibility of the negative here. So if we're looking at this, let's say we've got our plot, and let's put a mark at -5, and we put a plot or a mark at +5. Those are my vertical asymptotes, which I will denote with a green kind of dotted line. These are two lines that my function cannot cross. Okay. Now, I'm going to look at horizontal asymptotes, and again, I'm looking at end behavior. As x approaches infinity, or as x gets really, really big, what happens to y? Well, in this case, yeah, as x gets really, really big, the minus 25 really doesn't play much of a factor, so I can just kind of look at this piece, and y is going to tend towards 0. It's never actually going to get there, but it's going to get closer and closer. So if we now consider plotting some points, if we pick one to the right of our rightmost green line, so let's say 6. So 6 squared is 36, minus 25 makes 11. 1 over 11 is positive. It's above our horizontal asymptote line. So our chunk is going to look something like this. Now, similarly, if I do -6, which is to the left of the green, it's also going to be up above. Now, something interesting kind of happens with the middle piece. So sometimes it can come up and over the horizontal asymptote. The horizontal asymptote mostly is for the end. But when we're looking at this, how it's usually going to happen if I pick a number in between, let's say we pick 4 or even 0. If I pick 0, I'll have 1 over -25, which is below. So if I was to do a rough sketch of this, it would look something like this. Now, it is possible to have functions that can potentially do something like this. So they don't necessarily always have to be underneath the line with like these middle pieces. Really, it's these end bits that are really driven by that horizontal asymptote. But for now, what I've drawn in blue would be a potential good sketch of the graph that I've drawn here for this function. So that's one thing to consider. You're considering the end behavior, and in this case, not too crazy. But I have a couple examples here that we're going to talk about that are going to make things a little different. So let's change things up a little bit. Let's say I want to graph y equals x squared plus 1 divided by x minus 2. And I think this one would be pretty easy to see. Okay, let's go ahead, take a look at vertical asymptotes. I can't divide by 0, so when x minus 2 is equal to 0, that's going to cause problems. That would tell me I got a vertical asymptote at x equals 2. So if I was to draw my coordinate grid, +2, I cannot cross that line, period. Okay? Well, now I got to sit here and I got to think, okay, horizontal asymptote, what do I look at? Well, as I kind of mentioned in the last video, all we really have to look at is these leading terms up here. Because as x gets sufficiently large, let's say millions, this +1 and this -2 really aren't going to do much. So this function is going to very much mirror this function, x squared over x, as x gets big enough. Because eventually the +1 and the -2 just really aren't going to be affecting it much. If I'm talking millions upon millions upon millions, if I take 1 away from 10 million, not really taking much away there. Which then I can reduce this to be x over 1 or just x. And if we think about x, just y equals x, that doesn't have necessarily a single number that it tends towards. So if I think about as x approaches infinity, y is also going to approach infinity. And then if I think about as x approaches negative infinity, y also approaches negative infinity. So that's going to make things a little different, and what this function is going to look somewhat like, because I don't really have a horizontal asymptote to work with, it'll look something like this. And what's going to happen here is what's called an oblique asymptote, and this is something I never ask my students to find, but this does exist. It kind of creates like a slant asymptote. The idea here, again, is I'm just trying to help you establish a quick mental picture of what this thing should look like. It might be shifted a little more. It might be a little more like this and like this. There may not be necessarily an oblique asymptote. That's at least easy to see. But once you have graphing software available to you, you can plug it in and just roll with it. It's pretty easy to, GeoGebra is a free app. You can plot this thing in no time flat if you need an exact graph, but the ability to make sure it makes sense to you and make sure that the graph makes sense is important. So the way a lot of textbooks will teach this is that if you consider the degree of the numerator versus the degree of the denominator, if the degree of the numerator is greater than the denominator, then there will be no horizontal asymptote. Suppose I should write that. So there was no horizontal asymptote here necessarily because my number or my function is not tending towards a singular value. The last example, it was 0. This one's just going off towards infinity. Now let's look at a slightly different case. So again, if I'm looking at this, I'm thinking, all right, let's find our vertical asymptotes. That's pretty simple in practice anyway. It's whenever 3x minus 7 equals 0, which means that if I add 7 to both sides, x is going to equal 7/3. So 2 1/3. So all right, let's say there's 2, then I have my vertical asymptote roughly there. Let's say this is 7/3. Okay? Now let's think about a horizontal asymptote. I'm basically asking the question, okay, as x approaches infinity, what happens to y? Okay, well, if I think about what kind of happened with the last one, I didn't really care about the 1, I didn't really care about the 7, I only cared about my leading terms. So this is going to very much mirror what happens with 2x over 3x, which I can reduce that to 2/3. Now that tells me that this is going to be my horizontal asymptote at 2/3. So let's say this is a 2/3 mark. My values are going to be tending towards that value. Or my numbers in my function as it increases are going to tend towards that value. And that would kind of make sense because if I allow x to be millions upon millions upon millions, yeah, I'm going to take, let's say, 1,000,000. 2 million plus 1 divided by 3 million minus 7. Well, the plus 1 and the minus 7, they do just enough to make sure that it's not 2/3, but it's going to be very, very close to 2/3. So again, we'll test values here. And if we test the values, we'll find that the right chunk is above and the left chunk is below. And we could test them the same way. We say, okay, what happens when x is, say, 5 versus what happens when x is 0? And it'll kind of approach this 2/3 mark. So the way textbooks will approach it is if the degrees are equal, you can look at the leading coefficients. So in this case, 2/3. Whatever method you decide to use is fine, and I'll probably put together a slide here just kind of symbolizing it. I prefer to think of it in end behavior because then I only have to think one thing. I don't have to change it up depending on the degree of the numerator. So here's a quick reference to the more textbooky recommendations. if you're looking at horizontal asymptotes, the way it's presented in most textbooks is if you look at any given rational function, a of x over b of x, where a of x and b of x are both polynomials, if the degree of a of x is less than b of x, then 0 will be your horizontal asymptote. And this is kind of what we see when we talk about, say, 1 over x, or even if we have x plus 1 divided by x squared minus 144. They will both have the same asymptote, and that would be the axis line, the y equals 0 line, because as x gets sufficiently large, this term down here will eventually dwarf anything else around it. So moving on to the next piece, if the degree of a of x is greater than b of x, then there will be no horizontal asymptotes. This is just like that example we saw where we had x squared plus 1 over x plus 2, or maybe there was a minus in there. But the idea is that, again, this x squared term eventually is going to just dwarf everything around it. Therefore, it's going off towards infinity. Or it could even potentially go off to negative infinity if there was like a negative out front. The idea being that the degree will dictate kind of what happens at the end. And then likewise, we saw this with our last one if we had 2x plus 1 over 3x minus 7. If the degrees are equal, then I can look at the leading terms. Now that's the way most textbooks will present it. Like I mentioned, I personally am not a huge fan. I look at end behavior because it's just one thing for me to consider. But if this is more your cup of tea, this is a way to think about it. You can look at the degrees, and once you look at the degrees, you can theoretically know where your horizontal asymptotes are going to go. Now, I'm not a huge fan because I can never keep straight weight. I mean, is this the one where it was 0? Is this the one where I use the ratios? Or is this the one where they're the same? It's a lot to keep track of all at once, as opposed to if I think end behavior, I just have to answer the question, okay, what does x do if it gets big? Where does my y value go? And if you follow that, that will also kind of give you the idea of where end behavior is going. So, food for thought. Whatever method you choose is fine.